Beleza.
Ok, estamos gravando. Então, Gabriel, fica à vontade aí para falar. E, pessoal, quiser interromper no meio, pode interromper, beleza? Só vou pedir para todo mundo desligar microfone e câmera, mas se quiser interromper, fica à vontade para a gente fazer perguntas.
Okay, so hello everyone. Today I want to present some stuff me and Gabriel have been working on, and in particular we have been interested on how to apply Bayesian inference on collisional thermometry. So to begin with, I would like to give a brief motivation for the problem and also a quick overview on the general structure of the presentation. So I want to begin by asking ourselves a really practical question. How can we measure temperature on quantum systems? And I think the motivation here is both theoretical and also deeply experimental, because it's pretty useful to be able to measure and control temperature with high degrees of precision, especially in ultra-low temperature quantum experiments. And I think this question poses a challenge, essentially because temperature itself is not observable. So your measurement strategies and estimation strategies must be indirect. So you must find ways to indirectly estimate the temperature. So with that in our minds, one way to picture the typical thermometry protocol is like this. So you have some kind of model, and within this model, you have some bath. And since you usually don't have direct access to the bath, you have to couple this bath with some kind of probe or ancilla, and you engineer this model in such a way that you can encode this temperature dependence into the ancilla. And that's what you measure in practice. And okay, after you construct the model, you have to develop some kind of protocol to decide how you measure these ancillas, and then you acquire some data. And after you get this data, you have to choose a way to process it. And after processing this data, you will effectively discover something about the system. You can estimate, you can perform estimations. And I think that look at this diagram, it's easy to see that we could focus on two parts here. So we could either focus on how to optimize the model and the protocol. So we could try to find the best way to construct a model and the best way to get the data from this model, or we could focus on the second part here. So since data processing is a challenge hard enough, we could rather focus on how to optimally process the data to best perform an estimation on the system, on the parameters. So here the data is given, and we are just trying to find a way on how to manipulate this data. And our work's more in this direction. But before going into that, I want to give a quick intuition on the model we are using on the next slide. So we are going to use a collisional model, which was used on one of Gabriel's previous works. And in this model, we have a bath and a system. And the system will be a qubit. And we'll actually then interact. So the interaction of the bath with the system, which is simply a two-level system, is given by a standard Lynch-Blatt master equation. And just like we saw in the diagram, we don't have direct access to neither of them. So what you do is that you put an ancilla down below and a qubit, and you let this ancilla interact with the system. This interaction is given by a partial swap. So they exchange excitations. And note that you can tune both the time of interaction between the system and the environment, and you can also tune the time of interaction between the system and the ancilla. But of course, it's virtually impossible to discover anything meaningful about the system with a single measurement. So instead, we have a continuous string of ancillas. So we have a lot of identical copies. And after the first ancilla interacts with the system, we move it away, and we come with a detector. And then we measure the ancilla. So after measuring the ancilla, we can get a result, which is either 0 or 1, since this is a two-level system. And we store this value, this result, in a list or string, whatever. And then you can just keep repeating the same interactions. So you let the BF and the system interactions again. Then the system then ancilla interacts through the partial swap. You move the second ancilla away. You measure it, store the value, and you can just keep repeating this strategy for a really long time. So, and we can give names to both the interaction and this vector with the results. So this vector with the results, we call the detection record. I think it's important to remember this name. It will be the letter G all throughout the presentation. And we also have something called the stroboscopic map. It's just a formalization on how this discrete and alternating interaction works. So you can see that you have a thermal map, which acts on the system, and then we apply unitary to the joint density matrix, and then we can trace the ancilla out to get the state of the system. So okay, the idea here was to give a more of an intuitive picture. So now I want to formalize the idea a little bit more. So I think the really fundamental aspect of this model is the stroboscopic map, because this will dictate both the dynamics and also the associated distributions to the model. And there's also a little detail here, which is we actually don't measure the ancillas from the get-go. So instead, we will wait until the system reaches the steady state, and only then we will begin to perform measurements on the ancillas, because this will introduce a lot of analytical simplicity to the problem and a few symmetries, so it's easier to handle the system, the measurements, and so on. And another nice thing about this model is that you can perform both local and both joint and local measurements. So we can measure a lot of ancillas at a time, or we can measure just a single ancilla. And here in our analysis in particular, we'll focus on the simplest case where we measure a single ancilla at time, and we also ignore correlations. So in practice, the outcomes here will be all independent of each other. So they are IIG. Okay, so going to the next slide. I think that going back to our diagram in the beginning, we can see that we could maybe try to optimize the parameters of the model. So we could try to mess with the interaction time of both the system and the BEF. And we can also try to choose the POVMs in an optimal way to get the best measurements possible. And this was actually done before in the paper by Gabriel and his colleagues. So this won't be our focus here. We are just going to check if some of our results agree with them, but our contribution is different, because if you remember the diagram, we could do something different here. So we could try to focus on the parameter estimation part. So how can we effectively process the data? And to answer that, we also have to know how to define and construct estimators. How can we evaluate these estimators? How can we decide whether estimator is good or not? And we also can check whether there are any type of suitable bounds for this problem. And one way to tackle this problem is to use Bayesian inference. So before getting too technical, I just want to give a brief review on Bayes' theorem and how this works. So the idea here is the following. The question which Bayes' theorem answers is this one. So how can you infer something about the parameter given the data from your experiment? So the idea is the following. You have some type of joint probability distribution for the temperature and the data, and you can decompose it in this symmetrical manner using the conditional probabilities. And if you rearrange this equation, you get something like this, which is already Bayes' theorem. And each term here is a very precise interpretation. So what this term here on the left hand tells us, it gives us is the probability distribution for the temperature given the data. I'll get back here later, but first I want to begin with the right-hand side. So the idea here is the following. We have the prior with a previous probability distribution for your parameter. So it represents our initial state of knowledge about the temperature. So maybe for some physical or experimental reason, you know that the temperature maybe is inside a certain range of temperature. The nice thing about this framework is that you can always encode this type of knowledge into the prior. So maybe your prior is a flat with some kind of cutoff. Maybe it's a Gaussian around a certain value. There are many choices that you can make here. This term here on the left is the likelihood, and it's effectively the model for the system. And what this probability gives you is how likely you are of observing the data if the system were to be at a certain temperature T. So in our case, the likelihood is simply the chances of measuring the ancilla either in the ground or the excited state for a given temperature. And this term here down below is essentially just normalization. In some books you see it with the name of evidence, and in practice it's a marginal distribution. So what this probability tells you is how likely you are of observing the data, but irrespective of the temperature. So how likely you are to get a certain detection record, no matter the value of the temperature. And probably the most important part here, and it's what we want when we are performing parameter estimation, is what we call the posterior. So this distribution here is our updated state of knowledge about the system after we acquired the data. So if you got a certain detection record, what are the chances that the temperature is at a certain value T? So one way to look at this is that the posterior is essentially the likelihood, but backwards. So in that likelihood, you know the temperature and you want the probability for the data. And here it's the reverse. So you have the detection record and you want to construct a probability distribution for the temperature. So maybe this was a bit abstract. So I want to begin with a practical example. So imagine you have a cubist in a thermal state. So the density matrix is something like this. And the probability of measuring the cubist in the ground state will be this lower entry of the matrix. And the probability of measuring the system in the excited state is the upper entry in the density matrix. So in practice, you can write the probability distribution just like a binomial, like this. And the outcomes are either 0 or 1s. So if you plot these distributions, you get something like this. So the curve in orange is for the ground state, and the curve in blue is for the excited state. So what you can do here is the following. We want to try to apply Bayes theorem here. So the first thing we need is to identify the likelihood, which is this plot of the ground and the excited state. And just like I said before, this plot will tell you how likely you are to measuring the qubit in either of the states for different values of the temperature. So we can see that this function here will always be we always depend on the temperature. And the second thing we need is the prior. So choosing the prior may be a bit harder because there's always some degree of subjectivity when choosing this distribution. So we could, for example, choose a Gaussian, but in our particular case, this is not very physical. So another alternative is choose a flat prior. So there's some technicalities here, but in most cases, a flat prior is one way to reflect some kind of degree of ignorance about the system. So what we are saying here is that before making any measurements, we believe that all values of the temperature are equally likely. And okay, so now that you have decided on the likelihood and on the prior, we have to perform a measurement to get a posterior, so to get a distribution for the temperature. And we do the following. So suppose the result of the first measurement, you get a qubit in the ground stage. So the idea here is you take this orange curve and you put here in the place of the likelihood, and then you simply multiply it by the prior, and then you normalize the resulting distribution. So the posterior we get after the first measurement is something like this. And the challenge now is to keep updating the distribution as you get more data. And we do something called sequential updating here. So suppose the second measurement is also in the ground stage. So the likelihood will also be the orange curve, will again be the orange curve, but the prior changes. So we do the following. Our current posterior, so our current posterior becomes the new prior. So we take this term and put it here. And then we simply multiply by the likelihood. So we can see that the posterior changes again. So now we have the posterior for these two measurements and not a single one. And we can keep doing that. So suppose the third measurement is in the excited stage. So the likelihood this time around is the blue curve. And we take the posterior and put in the place of the previous prior. And the posterior will change once again. And here on the bottom right, I'm just drawing a dashed line to keep track of where the maximum of this distribution is. So it's the value of t which is more likely to be true. So, okay, you can keep repeating this strategy, and after a really long time, the posterior starts to peak around the true value of the parameter. And there's a really nice result, which we won't prove here, but you can say that in most of situations, this posterior actually becomes a Gaussian with the peak around the true value of the parameter in the asymptotic limit. So, okay, now I want to use the slide as a link to show some of our first results. So going back to our model.
Gabriel, can I ask you a question?
Of course.
So in the previous example, and so far, did you assume anything about the ancilli, about the state of the ancilli?
No, that actually wasn't even the same model. We were just forgetting the model for a while, and we were supposing that we had a qubit, but we didn't make any more physical assumptions because let me go back to the previous slide. So
maybe I didn't understand something. Okay.
So here it's just an example on how to use this. It's not true for our particular model because the ancilla won't necessarily be in the thermal stage. Actually, in most cases, it won't. And only for long interaction times. Here, what I'm trying to show is just how to perform, how to use Bayes' theorem given the density matrix. So given a stage, but it's not particular for our model.
Okay, so at this point, your rule of TH does not have anything to do with the setup that you showed. Yeah, okay.
Yes, sorry about that. Maybe I should have
no problem.
A little bit more clear.
Thank you.
But now I will try to show this type of distribution for our model. So now it's indeed for our ancillas. So what you do here is the following. I will choose a flat prior for the temperature. It's not exactly flat because I'm saying that it goes to zero in the edges, but that's just a technical detail. I don't think it's worth going into that. And we also fix the interaction time both with the batch and also with the system, the ancilla. So I consider that here we have a full swap. So we completely swap the state between the system and the ancilla. And if we use Bayes' theorem here, we get this kind of plot. So this is a density plot. This axis here on the horizontal is the number of measured ancillas, and each vertical slice on this plot is is the posterior after any measurements. So for example, this plot here is the posterior for n equals to 100. This plot here is the posterior for n equals to 200, and so on. And you can see, I hope it's visible to you, but this density starts to peak around the true value. So here we fix at 1.5, and we see that it starts to get yellow around this value because the posterior starts to peak around it. And here on the right side, I'll just show a quick animation to give you an idea on how this density evolves with time or with the number of measurements. So the evolution of the posterior would look like something like this. So, okay, I showed you a bunch of posteriors, but I didn't give any practical insight on how to use and construct estimators. So that's what I want you to do now, because you can use these posteriors, you can use these densities to have a answer which is more concise. You can give a number, you can give an effective estimation, because giving just the distribution is not always useful. So effectively, you want a number as an estimation. And that's what estimators do. So one really simple way to define estimators is as random variables, which depends on the outcomes of your experiment. And you want to choose this function to estimate some parameter about the system. And in our particular case, I want to introduce the notion of Bayesian estimators. So we say that a Bayesian estimator is an estimator which minimizes some type of Bayesian error or risk function. And these functions typically will look like this. So it should depend on a coach function, and this coach function tells you how to penalize errors. And you take this coach function and you integrate both over the results, the trajectories, and over the data, and also over the parameters. And this is something which is quite different from the usual frequency approach and what we typically see in thermometry, because in the frequency approach, you usually consider that the parameter is just a constant. It's a value that you don't know, but it's fixed. And that changes in the Bayesian framework. Now we consider that the parameter is also a random variable. So in a lot of equations, you see integrals, it's kind of double integrals, so having an integral both over the data and also over the parameter. And one thing I want to show here is that different type of estimators will minimize the error for different coach functions. So just to illustrate, suppose you have some prior, you perform some measurements, and you get posterior, just like in our previous examples. The question now is how to use this posterior to construct estimators. And there are a few ways to do that. So if the coach function is the uniform coach, so this is like as either 0 or 1, the mode, the Bayesian estimator here will be the mode of the posterior. So you just take the peak of the posterior, and this will be your estimation for the temperature. So it's the dashed line I showed in the previous example with the qubit in the thermal stage. So okay. If the coach function is the absolute coach, so it's just the absolute difference between the estimation and the true value of the parameter, the Bayesian estimator will be the median of the posterior. And if we instead use the squared error as the coach function, the Bayesian estimator will simply be the mean of the posterior. So I use the acronym BA here for Bayesian average. And for the next few slides, I want to stick with this estimator in particular, because it's really easy to work with, and it also has a lot of nice analytical properties. So most of estimations from now on, we're gonna use this estimation here. So it's really simple to see how this works. We can simply pick the plots in our previous slide because we already have this posterior, and then we integrate over the temperature to get an estimation. So if we do that, we get this kind of plot. So here you can see the dashed line in black, which is the true value of the temperature, and we have two curves here. In red, it's the mode of the posterior. So we call it the mapping because it's the maximum a posteriori. You take the posterior and maximize it, find the maximum, and then you plot it as the estimator. And in blue, we have the Bayesian average, the estimator on the left side of the screen. And we can see that in the asymptotic limit, both of them will converge to the true value of the parameter. And we can also try to plot, we can now take the estimator, plug it into this expression here, and try to plot to calculate the error for these strategies. So we can do the following. Let me just rearrange some stuff here. So now we can plot the error. In this particular plot, I'm still not plotting this Bayesian risk because it's actually a conditional error. So I am plotting the error for this particular value of the temperature. So we are fixing the temperature at 1.5 in units of frequency, of the qubit frequency. And here, there are three curves here. So there's a gray stochastic curve here, and this curve is just the error for this particular realization on the right side of, on the plot on the right hand side of the screen. So if we take this estimation in blue here and calculate the error just by taking the difference with the true value of the parameter, we get the stochastic plot on the gray stochastic plot on the left side. And which we can also try to integrate all these stochastic trajectories over the data, just over the data, not on the parameter, but just this inner integral on the data to get a curve like this blue one here. So this blue curve is the error, but in the frequency sense. So it's the error conditioned for this particular value of the temperature. So we get this blue curve, and we can see that in the asymptotic limit, it will start to converge to the Kramer-Hall bound, which is this dotted line here. And I think that it's then clear that the error, even if we integrate over the data, it will depend on the temperature. So I want to show something along these lines. So here in this plot, I'm showing the conditional error in the frequency sense for different values of the temperature. So on the bottom, for instance, we can see that the error is smaller for lower values of the temperature, and it's higher for bigger values of temperature. And to effectively get this Bayesian risk, one way to do this is to take this plot and simply integrate or take the average over all these temperatures, and we get something like this on the right. And this plot here on the right is indeed the Bayesian error, the Bayesian risk. So it's the error integrated both over the data and also over the parameters. So this is like a really concise and really neat way to show how your estimator is performing for all type of trajectories, all type of detection records you can get, and also for different values of temperature, because you can, for example, have an estimator which works really well for a certain range of temperatures and works really bad for others. So the Bayesian risk is like a really concise way of taking all that into account into a single plot. And here we can see the curve on red for the map, for the posterior mode, and also the curve on the blue, which is this estimator here above, which is the Bayesian average. And you can see that our result is at least consistent with our result which is the Bayesian average, will be the best estimator in the squared error sense. So using this coach function, this estimator here is the one which will give the smallest error possible, even though all of them in general will be more or less the same in the asymptotic limit. So do you have any question?
I have a question. So,
Okay,
but
Marcelo.
if you're going to answer in the future, please. So what I keep thinking while looking at that is that how do you actually control whether like your probes are not drastically modifying your steady state? Okay. Did you understand?
Yes. So I think that in practice, by steady state, Marcelo, by saying that the system in steady state, we are already taking that into account, because if you remember the definition, the steady state is not only taking the interaction between the bath and the system into account, but it also takes the interaction between the system and the ancilla as well. You know, so every time you let the system and the ancilla interact, the system will kind of go back to the steady state in the next step.
But in any case, if your steady state already accounts for that, it means that it's not like what you are probing has some influence of your choice of ancilla, right?
Of course. For example, depending on the choice of the ancilla initial stage, you change the quality of the estimation, so you get different results. Of course.
Yeah, that's my point. So how do you make this choice?
So there are a few ways to do that. The simplest way would be to just test with different states, but instead what you can do is you can just calculate the future information for different choices of parameters, because you know that in the limit of a high number of measurements, the estimation will converge to, the error will converge to the reciprocal of the future information. So, for example, in all these plots here, the error is converging to the Kramer-Hall bound.
So maybe can I add something, Gabriel? Sorry.
Of course.
So Marcelo, this was kind of the main issue we had in that collisional thermometry paper. So in principle, the initial state of the ancillas is arbitrary, and there's no rule specifying like which one is the best state. But we generally find that if we start the ancillas in a computational basis, that usually leads to better estimation. So it's better than to start it in like a coherent state or something like that. And so here we're kind of just using what we learned from the collisional thermometry paper. So we're already operating at sort of the optimal configuration.
Okay, nice. Thank you.
Oh, and by the way, guys, especially new folks, Alberto, Gabriela, Jefferson, and so on, please, if you have any questions, don't hesitate to ask. I mean, we're among friends here, so don't feel shy about asking questions. Okay?
I have one.
Okay. I didn't include you, Chico. No, you're not. No, just kidding.
Now, everything you guys are doing here so far, it kind of only works if you have a classical state, right? You need to have probability distributions that have no contextuality, nothing of the sort. Otherwise, Bayes does not really work like this, right?
So to be honest, I don't know much about contextuality, but
it's because the version of Bayes you're using assumes that you can build a joint distribution. So basically, you can. So
actually, I think we can, Chimpa. I think we can. We didn't do that much detail until now, but I think in principle we can also try to use this kind of formalism for joint measurements, for example. So for two ancilla density matrix states, and so on.
Yeah, because what I think is you're measuring one ancilla, right?
Yes.
The ancilla interacted with your system, and then you measure your second ancilla, right?
Okay.
So there must be some correlation between the two measures, right?
Yes, yes.
And are these correlations classical or quantum? That's basically what I'm asking.
Yeah, I don't know the answer. We know that there are correlations, but I'm not sure how to decide whether they are quantum or classical. I don't know.
So
I'm not so sure if you can do things like this if the correlation is quantum. That's what I was. I think it would be a bit. I think it would need to be something a bit more sophisticated, the treatment, if the correlations are quantum, right?
No, so the point here is that these outcomes are really probabilities, real probabilities, which are the outcomes of actual experiments. If you want to get classical correlations, you would actually have to do global measurements, so collective measurements on 2 or more ancillas. But here, you're right, Chimpa, we're doing local measurements, so we locally measure each ancilla. And so in the end of the day, we just get outcomes X1, X2, X3, which are just classical outcomes of these local experiments. And there are correlations between them, but these are just our classical correlations in the end of the day. So yeah.
Oh, okay, so yeah, so there's nothing fishy here. Okay.
There's nothing fishy here.
Yeah. Also, as far as I understood, once you measure like the ancilla, you are erasing the non-local correlations, right? The non-local coherence, I mean.
Yeah. Mm-hmm. Exactly.
So, okay. Any more questions?
Are you hearing me, Gabriel?
Okay. Moving on. I think we are really almost done. There's just one last thing I want to comment on. So, one problem with trying to use this Bayesian framework is because we can't use the typical non-Bayesian bounds anymore. So we can't really use, for example, the usual Kramer-Hall bound. So the Kramer-Hall bound is a bound for the variance of an estimator. Maybe, sorry, I should have used chi instead of theta, but the theta here is just a parameter as well. And in our case, there are a few problems. It's of course not wrong to use it, but if we try to use this bound with our framework, there will be some inconsistencies. So we have to try to solve that. So the first thing is that this bound depends on the parameter at hand. So it will be parameter different. So depending on the value of the temperature, you get different bounds. And it's not so much restriction because I know that you can generalize the Kramer-Hall bound for this case, but in this particular form here, the Kramer-Hall bound assumes some biased estimators. And one last thing, and I think this is even more glaring, is that it's not clear what kind of role the prior plays here. So suppose beginning with a prior, it's super delta-like. From the get-go, just from the first measurement, you already have a really, really small variance. So you can kind of violate this bound really, really easily, depending only on the choice of prior, for instance. And not only that, maybe this prior is super delta-like, but at the wrong value. So the variance is small, so the error is big, because your estimation is quite biased. So the bound won't give you anything meaningful. And the idea here is that there's some type of analog of the Kramer-Hall bound, but for the Bayesian framework. And we call this bound the Venturi's inequality. So the first thing we have to do here is, instead of using the variance, we use the mean squared error in the Bayesian sense, averaging both over the data and the parameter. And by doing that, we can construct a bound for this error. So the Venturi's inequality looks like this. And we can solve both of the previous problems. So this term here is simply the Fisher information for the prior, So we take into account the initial information that the prior gives us in this bound. And the second term is the mean feature information. So it's somewhat similar to the Krumer-Hall bound. So this inner integral here is just the feature information for a particular value of parameter theta. In our case, it's the temperature T, but it's averaged also over the parameters. So in practice, this is the mean feature information averaged over all the parameters. So it's bound, it will not depend on a particular choice of temperature or any other parameter. It will just depend on the prior you choose and on the likelihood, which is essentially the model you are using.
Sorry, Gabriel, can I make a quick comment?
Of course.
I mean, it's more than saying that it's average over the parameters, but it's really average over the prior, right? So it's
yes.
What you believe is the range of theta, so to speak. So it's like over your belief intervals, something like that.
Yes, of course. And okay, and I think the message to take home, not only for this bound, but for the Bayesian framework in general, is that it's been pretty useful for thermometry, because at the end of the day, you want a thermometer which is good for a wide range of temperatures and not a single value, so, or really particular range. And the Bayesian framework is a really concise way, a really niche way of constructing estimators and also evaluating them independently of a particular choice of parameters. So it's a really simple way to evaluate how well your estimation is performing for a wide range of cases. And now we are almost done. I just want to go back to the plot with the error. And if you try to push the Venturi's inequality here, it should look like this. So we can see that this bound, of course, will not be necessarily tight. So it may be actually pretty different in the asymptotic limit. And one last plot I want to show is actually the error, but varying the parameters on the model. So here I want to show the error for different values of swap time. So here in this plot on the left, we are simply changing the unitary interaction time, and we can see that for when the swap is weak, the estimator is in general worse, and when the swap time is stronger, the estimator is in general also better. And in this plot on the left, I am fixing the temperature at 1.5. So this is actually the frequency error. And on the right, we actually have the Bayesian error, so the Bayesian risks. So here we are averaging over the prior, over the parameter. And we get something like this. And here down below, we have the Venturi's inequality for each of these plots. So in blue, it's for the weak swap, partial swap, and in purple, it's for the full swap. And yeah, that's what I wanted to show. And just conclude, I think a few conclusions can make that the collisional models are a really simple model to treat analytically and natural platforms to perform thermometry on. And not only that, it works really well with Bayesian inference, because it's a simple way to construct a wide class of estimators. So we are not restricted to the type of estimations we can make. We can make a lot of different choices based on the type of problem we're dealing with. And it's a concise way of evaluating. It also provides a concise way of evaluating these estimators and to say how well they are performing for your model. And we also saw that you can construct Bayesian analogs for some frequency bounds without too much trouble. So for example, we can go from the Kramer how to the Venturi, for example. So there are a lot of kind of like extensions from frequency approach to Bayesian approach. And just one footnote I would like to make here is that there's of course no right or wrong here. So I don't think you can really say that Bayesian framework is better or that the frequency framework is better. They are just different way of doing things, and depending on what type of information you want or what type of model you are dealing with, it may be more convenient or more easy to work with some framework or with another. You see, for example, a lot of authors which use the Bayes theorem, for example, to construct estimators and so on, but their interpretation and their plots are all frequency, for example, and vice versa. So this is in no way better or worse what is typically done. It's just I think a different way of treating the problem, and it may offer some new insights depending on what you are doing. So that's it, everyone. Thank you for listening. If you have any questions, feel free to ask.
Oh, thanks, Gabriel. Anyone has questions?
Gabriel, when you so I wanted to kind of explore a little bit more this idea that you said about the prior, your assumptions about the prior. So you mentioned that your assumption of a almost homogeneous prior was due to like minimize the bias. Is that correct?
Not to minimize the bias, but it's a way to say that you are actually ignorant about the values of the temperature. So if you don't have any measurements, you don't know anything about the system, for example, one way to do that is to use a prior which is flat or something similar to that.
Yeah, that's what I mean precisely.
Okay, sorry.
Because yeah, that's the kind of the same reasoning behind like maximum entropy principles. If you don't assume anything about your system, you get like a flat distribution. If you assume you know something more, you start to get some kind of Gibbs probabilities. But that's the precise thing that I wanted to ask. If you can know something about your system, like by some kind of other experiment or something, and you can implement this knowledge somewhere in your model, maybe this would be at the prior. So
yes,
this is something, for example, you know that if the system is in the steady state, the energy does not change. But if you know this number, maybe you can implement in the model.
Yeah, I think that's one of maybe advantages or merits. You can do precisely that, Marcelo. You can encode all this kind of knowledge in the prior. So your estimation will be usually better from the start. But in our case, at least there weren't I think any type of symmetries to choose a different prior. So we stick with that for now. I'm not sure if that was the question.
Yeah, it was not really a question, kind of just idea.
Yeah, I think it's interesting that it's not always obvious what we should put on the prior, right? I mean, if you're trying to estimate temperature, it's reasonable that temperature should be, you should know the temperature at least within a range, right? I mean, we know that the temperature of a trapped diamond is not like 10,000 kelvins or something like that. So there is a range we can put there always. But if we can put something else, it's not so clear, and that's an interesting question. In physics, we don't worry too much about priors, right? Because we always assume we have like an infinite number of clicks, and so like the prior information is irrelevant. You just measure as long as you want, and in the end of the day, the precision that you get is irrelevant of which prior you started with. So this notion of prior in physics, we don't use it that much, I guess. But it would be interesting to see if there are other things we could include.
Yeah, I mean, like I was thinking about this kind of question in some days ago, and I think the closest thing of a prior that we have kind of in the quantum mechanics framework is the idea of the preparation, like the that's kind of one of the reasons that I also asked about the ancilla, because this is some of the kind of the things that are prior to your experiment, like the preparation. So that's something that's always interesting to explore too.
Right.
But yeah.
So, but
Yeah.
that would be kind of different in the sense that that would be, it's like an experiment conditioned on some preparation sets. But the prior here refers to the prior about the parameter, right? So I guess it is a little bit different in that sense, but I get the point.
Yeah, yeah. And also, by the way, very nice. I like very much the work.
Thank you, Marcelo.
Okay, more questions, everyone?
There was a question from Timpa that I didn't understand, but I found interesting. When you don't have you have quantum correlations, you can't use that form of Bayes theorem, or I didn't understand what was the point, but what do quantum correlations made different than classical in this case?
So maybe Chimpa wants to answer, I guess. It's better. Chimpa, you there?
I guess.
I
No.
guess not.
Wait. I hear. The thing is that when you use Bayes theorem, you're assuming that you can. You're basically assuming that you can measure the thing you want to infer something about, and the thing that you're conditioning about. That's not always the case if you have a quantum system, because you can have observables that are not joint measurable. So if it makes no sense to talk about a distribution of position given momentum, for example, because you can't measure position and momentum at the same time.
All right,
So you need to be a bit careful with the things. And since I'm talking, I have another question. This is, I think, maybe more a suggestion. Do you think that if you do things like this, measuring one ancilla at a time, you are kind of bound to how fast things can converge in a classical statistical sense? So it's always the error going to with 1 over the square of the number of measures that you made. Do you think that if you made a joint measure of ancillas, maybe tweaking maybe putting them through some unitary, I don't know, and make a joint measure, you could get something like 1 over n for something that 1 over the number of ancillas for the error?
We actually did some tests in this direction, Chimpa, but it's not anything really certain, because it seems that there's some kind of improvement, but at least for our choice of parameters, it wasn't anything really that significant. Because I think that for this model in particular, at least on collisional thermometry, actually the improvement from joint measurements from 2 or more ancillas actually are stronger, more significant for weak interactions. So for weak interactions between the ancilla and the system. So I think it should be more meaningful to maybe investigate it in around this domain, this choice of parameters. But for at least for the type of test I did here, there wasn't much improvement, I think. And another thing that is a bit difficult, and that's a problem. There are some works in that direction, but when you go to two or more ancilas, the optimal basis may depend on the temperature. So you have to find a way to choose a basis. It's not exactly easy to do that, because for a single ancilla using the probe states in the ground state, the optimal basis will always be the computational basis. So it's easy to work with this protocol for any temperature, but that may be not necessarily true for two or more ancillas. So it's a bit harder to generalize in that direction. I'm not sure if that was the question.
No, it was more of a suggestion, but I think if there are papers already in this direction, then I think you're aware of it.
So just to further elaboration, actually up until now, I didn't see any papers which made something more explicit like this using Bayesian inference, actually in thermometry. But there was a PRA from 2017, which me and Gabriel just read last week, in which they tried to generalize the ideas of quantum feature information and so on using this Venturi's inequality and this kind of stuff. So instead of writing the quantum Kramer-Hall bound, they try to write like a quantum Venturi's inequality. And the difficulties of extending the concepts are in this direction. And actually, until now, I didn't see any works based on this paper with more practical suggestions on how to do that. So I am not sure if it's entirely trivial. And that's why, at least for now, for the beginning, we were sticking with single ancilla measurements.
Okay.
Gabriel, I have a question. So you mentioned when you showed the Venturi bounds in comparison with the other ones, you mentioned that it's not necessarily tight. I mean, did you see in that Venturi's book or something saying something about like when can the bound be tight? Is it never tight, or are there situations where it can be tight?
So I can try to sketch something. I hope it works. But let me quit the presentation. Okay. But the reason for that is essentially Jensen's inequality. So I'll try to quickly sketch something here. Which works. So stop it working. So sorry, I'll try to speak to explain with words.
No problem.
So let me see. So, but in the Kramer-Hall bound, what you have is the 1 over the Fisher information, right? Yeah. So if you take the average, kind of the average over the Kramer-Hall bound, so we take the average over the asymptotic limit for different values of the temperature, you have like the expected value of 1 over the Fisher information. But what appears into the Venturi's inequality is not that. It's 1 over the expected value. So you can use Jensen's inequality to show that in general the Venturi's bound will be tighter than the mean of the Kramer-Hall bound. So that's why this curve not tight. They only coincide when the Venturi's information, when the Fisher information does not depend on the parameter.
Right. Right. Okay. Okay, that's cool. More questions? No? Okay, then I guess that's it. Thanks, guys. Next week we have Marcelo's talk. Thank you. See you Friday, actually.
Thank you, everyone.
Yeah.
Tchau, gente. Feliz dia do
Tchau.
físico.
Verdade.
Valeu, pessoal.
Valeu.
Tchau.
Tchau,
Até
tchau.
mais.
Parabéns, Gabriel.
Obrigado, Ney.
Mas...